तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the first lecture of Module 7 on transmission of prestress. In this lecture, after the introduction, first we shall study about pretension members, and in today's lecture we shall just cover the pretension members. For those type of members, we shall learn about the transmission length, the development length, and the end zone reinforcement. In a prestressed member, the prestress is transferred from the steel tendons to the concrete. Now, the mechanism of the transfer of stress from the steel to the concrete is different from a pre-tension member and a post-tension member. The stretched tendons transfer the prestress to the concrete, leading to a self-equilibrating system. The mechanism of the transfer of prestress is different in the pre-tensioned and post-tension members. The transfer or transmission of prestress is explained for the two types of members separately. First, the pre-tension members. For a pre-tension member, usually there is no anchorage device at the ends. The following photo shows that there is no anchorage device at the ends of the pre-tension railway sleepers. In this photograph, you can observe that the strands have been cut and there is no anchorage device at the end of these railway sleepers. This is an essential difference of the pre-tension members as compared to the post-tension members. For a pre-tension member without any anchorage at the ends, the prestress is transferred by the bond between the concrete and the tendons. There are three mechanisms in the bond. First is adhesion between concrete and steel. This occurs due to some chemical reaction at the interface. The second is the mechanical bond at the concrete and steel interface. And the third is the friction in presence of transverse compression. Out of these three components, the mechanical bond is the primary mechanism in the bond for indented wires, twisted strands, and deformed bars. The surface deformation enhances the bond. Thus, out of the three mechanisms, the adhesion, the mechanical bond, and the friction, out of these three, it is the mechanical bond which is usually the primary mechanism of bond. Now, to enhance this mechanical bond, the surface of the steel is provided with some deformations so that the bond between the steel and the concrete is better. Let us now see three examples of the surface deformations. In this sketch, you can observe that the wires have been provided with some indentations. The indentations can be circular or they can be elliptical. The indentations are provided at a certain pitch, and this type of wears are better than the plain wears regarding the mechanical bond. For a twisted strand, say a 7-wear strand, the surface itself is quite deformed because of the individual wears twisted around a central wear. Hence, the mechanical bond in a twisted strand is much better than a plain wear. And if a deformed bar is used for pretensioning, there also we find that the surface deformations in the deformed bar helps in having additional mechanical bond in the concrete and steel interface. The prestress is transferred over a certain length from the ends of the members, which is called the transmission length. Now, this is a very important concept for a pretension member, that the prestress is not transferred right at the ends, but it is transferred over a certain length from the ends, and this length at each end is called the transmission length or the transfer length. Here we shall denote the transmission length as LT. The stress in the tendon is 0 at the ends of the members. It increases over the transmission length to the effective prestress, which is FPE under service loads, and remains practically constant beyond it, neglecting the losses due to friction and wobble. Thus, that in a pretension member, the stress at the end of a prestressing strand is 0. It increases to a value of FPE for service loads along the transmission length, and beyond that it stays more or less constant. Now, when the load is applied, then the stress may increase from FPE to a higher value depending upon the amount of load, but that increase is substantially less compared to the increase over the transmission length. This sketch shows the variation of the prestress in the tendon, that the prestress varies substantially in the transmission length at the end. Under service loads, it increases up to FPE and then it stays more or less constant. The increase in the prestress can be assumed to be parabolic, which has been determined from experimental tests. Next, we shall talk about the Hoyer effect. The Hoyer effect that develops in a tendon is explained. After stretching the tendon, the diameter reduces from the original value due to the Poisson's effect. When the prestress is transferred after the hardening of concrete, the ends of the tendon sink in concrete. The prestress at the ends of the tendon is 0. The diameter of the tendon regains its original value over the transmission length. Let us try to understand this Hoyer effect by the example of a few sketches. The change of diameter from the original value at the end to the reduced value after the transmission length creates a wedge effect in concrete. This helps in the transfer of prestress from the tendon to the concrete, and this is known as the Hoyer effect. In this sketch, the tendon has been stretched, its diameter has reduced from the original value due to the Poisson's effect. That means, after stretching, the diameter of the tendon is less than the original diameter of the tendon. Next, the concrete is poured and it is allowed to harden, and after it is hardened to the requisite strength, then the tendons are cut and the prestress is transferred to the concrete. In this process, the tendon slightly sinks within the concrete and the stress at the end drops to 0. Now, in this sketch, what we are observing is that the concrete has been cast, the tendon is about to be cut. At this point, still the tendon has its diameter constant throughout the length, but after this, when the tendon has been cut, the end of the tendon has sunk by a certain distance, the stress at the end has dropped down to 0, and since the stress has dropped down to 0, the diameter at the end has regained its original value, and over the transmission length the diameter reduces due to the Poisson's effect, which is still retained as the prestress is increasing over the length, and this change in diameter from the original value to the reduced value over the transmission length creates a wedge effect in the concrete. That means that there are forces which is not allowing the tendon to move inside the concrete any further, and in reaction to this, the prestress tendon is applying the prestress to the concrete. Right after transfer of prestress, the prestress beyond the transmission length is Fp0. With time, after the long term losses, this value of Fp0 will drop down to the effective prestress Fpe. The higher effect is beneficial for the transmission of prestress from the tendon to the concrete. Since there is no anchorage device, the tendon is free of stress at the end. The concrete should be of good quality and adequate compaction for proper transfer of prestress over the transmission length. That means the transfer of prestress is solely depending on the bond between the concrete and the steel. The concrete has to be of good quality and adequate compaction to have a strong bond at the transmission length over which the prestress is transferred from the steel to the concrete. Hence, the quality and construction of concrete should be paid attention to. Next, we shall discuss the measurement of transmission length, because we need to have an estimate of the transmission length to make sure that as the prestressing is developing over the transmission length, we are not placing high demand on the prestressing tendons. There are several factors that influence the transmission length, and these factors are as follows. The type of tendon, whether it is a wire, strand or bar, and we have observed earlier in the sketches that each of these tendons has a different type of surface deformation, and hence the transmission length is different for this type of tendons. The second factor is the size of the tendon. Are we having a single wire or are we having a cluster of wires? That depends upon the size of the tendon, and hence you will observe that for a smaller size we have larger perimeter, and hence the bond developed is better for smaller wires. Then the third factor is the stress in the tendon. that if the applied prestress is high, then the transmission length required will be also high. And we have to be careful that we have adequate provision of this transmission length in the member such that the prestressing tendon has its prestress developed when the external moment demand is acting on the section. The fourth factor is the surface deformations of the tendon. As we have already said that the mechanical bond differs depending on the surface deformations. It is small for a plain bar, but for an indented, twisted strands or deformed bars, the surface deformations are more and the mechanical bond is also more. The fifth factor of the transmission length is the strength of the concrete at transfer. If the concrete is not of adequate strength and if it is not of good quality, then the transmission length will be also larger. The sixth factor is the type of loading, that if it's a point load or whether it is a uniformly distributed load, depending on that the transmission length can vary. That means that if there is a point load which is acting at one side of the member, or if it is a uniformly distributed load, then we can observe that the transmission length is different in these two cases. The seventh factor is the pace of cutting of the tendons, that when the prestress is transferred to the concrete, are we abruptly cutting the tendons by a flame cutter, or are we slowly releasing the jack and applying the prestress? It is found that the transmission length is smaller if we are slowly releasing the jack. That means there are these several factors which govern the transmission length. There are some more factors, like if there is some confining reinforcement to check the development of cracks, then the transmission is better. The effect of creep in concrete can also influence the transmission. As I said before, that the compaction of concrete is very important regarding transmission. A good compacted concrete will have a lesser transmission length and the prestress transfer will be better. And also it depends on the amount of concrete cover around the prestressing tendons, because if we have more concrete, then the prestress transfer will be better. Thus, the transmission length, since it depends on several factors, we have to estimate it by simple expressions to have an idea that what is the length over which the prestress is getting transferred from the steel to the concrete. The transmission length thus needs to be calculated to check the adequacy of prestress in the tendon over that length. A section with high moment should be outside the transmission length so that the tendon attains the design effective prestress, which is FPE at the section. In case if there is a point load very close to the end of the member, in that case we have to be very cautious that the point of high moment is outside the transmission length so that the tendon has the requisite length to develop the prestress, and the concrete also has the adequate prestress to counteract that moment. The code IS 1343-1980 recommends values of transmission length in absence of test data. These values are applicable when the concrete is well compacted, its strength is not less than 35 Newton per millimeter square at transfer, and the tendons are released gradually. The recommendations of the codes are simple. They do not involve the different factors that we have seen. These recommendations can be used provided we have a good quality concrete with adequate strength at transfer, and the tendons are released gradually. As per the recommendations of the code, for plain wear, the transmission length should be 100 times the diameter of the wear. For intended wear, the transmission length is smaller, which is 65 times the diameter, and for twisted strands, the transmission length is even smaller, which is 30 times the nominal diameter of the strand. Thus, here we can see that the only factor which is being considered in the transmission length is the size of the tendon. No other factor has been considered in this simple estimate. There are more involved estimates of the transmission length, which takes account of some more factors. Now, to repeat that the codal recommendations is applicable only when the concrete has been compacted properly, it has the adequate strength during transfer, and the tendons are released gradually. And we can observe that for a plain bar, the transmission length is higher, whereas for an intended wear or for a twisted strand, the transmission lengths are smaller. To avoid the full transmission length located near the clear span of a beam, IS 1343-1980 recommends the following: to have an overhang of a simply supported member beyond the support by a distance of at least half of the transmission length. As I said, that we do not want the points of high moment to come within the transmission length. For a simply supported beam, the points of high moment are usually within the span, but the code says that from the central line of the support, there should be an overhang at least of half the transmission length, such that when we cross the face of the support, by that time the prestress has developed in the concrete and the tendon has also regained its full effective prestress. If the ends have fixity, then the length of fixity should be at least LT. That means if we have inserted a pretension member in a socket and there has been some fixity at the ends, then the length of the fixity should be at least the transmission length, such that after we go beyond the face of the support, then the prestress has already been transferred to the concrete. These are the recommendations to check that the points of maximum moment are outside the transmission length calculated from the ends. Next, we are moving on to another concept, which is the development length. The development length needs to be provided at the critical section, the location of maximum moment. The length is required to develop the ultimate flexural strength of the member. The development length is the minimum length over which the stress in tendon can increase from 0 to the ultimate prestress FPU. The difference between the transmission length and the development length is that in the transmission length, we expect the stress in the tendon to develop from 0 to the effective prestress under service loads. Whereas for the development length, we expect the stress to develop from 0 to the ultimate prestress FPU, and the member should attain the maximum flexural capacity under ultimate loads at the end of the development length. Thus, the transmission length is required to achieve its service capacity, whereas the development length is required to achieve its ultimate capacity. If the bonding of one or more strands does not extend to the end of the member, which are called debonded strands, then the sections for checking development of ultimate strength may not be limited to the location of maximum moment. Sometimes the strands are debonded towards the end to reduce the effect of the stress concentration at the ends. In such a situation, the critical section to check development length may not be just the location of maximum moment, but we may have to check some other locations depending on the length of debonding of the strand from the concrete. Now, we will not consider debonded strands here because it is more of a case-to-case basis, and specialized literature may be referred to when we are working with debonded strands. In this lecture, we shall consider that all the strands are having bond throughout the length of the member. To come back to the development length which will be denoted as LD is the sum of the transmission length LT and the bond length which will be referred to as LB. Thus, LD is equal to LT plus LB. The bond length is the minimum length over which the stress in the tendon can increase from the effective prestress FPE to the ultimate prestress FPU at the critical location. Thus, LD is the length over which the stress in the tendon is developing from 0 to FPU. This consists of two components. One is LT, where the stress develops from 0 to FPE, and another component is LB, where the stress develops from FPE to FPU. The second component is called the bond length. The development length is significant to achieve ultimate capacity. That means whenever we are checking the member capacity at a particular critical location, we need to make sure that the adequate development length has been provided from the end to that particular location so that the stress in the tendon can achieve the ultimate prestress FPU. The following figure shows the variation of prestress in the tendon over the length of a simply supported beam at ultimate capacity. Here, the simply supported beam has been subjected to a uniformly distributed load. Around the center midspan, it is expected to have the ultimate capacity with the prestress equal to FPU. Here we can see that from the end, we need to have a certain distance LT to develop the stress from 0 to FPE, and after that it has to have the minimum length to develop the stress from FPE to FPU. Now, this stress needs to be developed at the critical section where the moment is maximum. The calculation of the bond length is based on an average design bond stress, which we shall denote as tau BD. A linear variation of the prestress in the tendon along the bond length is assumed. The following sketch shows a free body diagram of a tendon along the bond length. We are assuming that in the minimum length, which is denoted as the bond length, the increase in stress is linear, or in other words, the bond stress is constant. In order to evaluate the bond length, we consider a design bond stress, which is represented as tau BD, and in this free body diagram we can observe that on the left side of the tendon, the prestressing force is the effective prestress times the area of the prestressing steel, whereas on the right side, which has the ultimate capacity, the prestressing force is FPU times the area of the prestressing steel AP, and this is under equilibrium along with the bond stress tau BD, which is assumed to be constant over the length. If the tau BD is constant, then the increase in stress from FPE to FPU is linear over the bond length LB. Now, the bond length also depends on several factors. First of all, the surface condition of the tendon, similar to what we have seen for the transmission length. Here also we observed that the surface condition influences the bond length. The second factor is the size of the tendon, similar to that we have observed in transmission length. The stress in the tendon, what are the values of FPE and FPU that influences the bond length. Depth of concrete below tendon, that how much concrete do we have, and the more concrete we have, that is better for the development of the stress. Now, based on the free body diagram, we can write an expression of the bond length, which is in terms of the ultimate prestress that we are designing for FPU and the effective prestress FPE, the diameter of the tendon and the design bond stress, which is tau BD. Thus, the expression of the bond length is equal to LB is equal to within bracket FPU minus FPE times the nominal diameter phi divided by 4 times tau BD. This equation has been developed from the free body diagram of the tendon. Note that here the diameter is the nominal diameter of the strand that is used as the tendon. The value of the design bond stress tau BD can be obtained from IS 456-2000 clause 26.2.1.1. The table is reproduced below. The design bond stress for plain bars is, for M30 concrete, tau BD is equal to 1.5 Newton per millimeter square. For M35 it is higher, it is 1.7 Newton per millimeter square. For M40 and above, the tau BD is limited to 1.9 Newton per millimeter square. Thus, for a particular pretensioned member, once we know FPU and FPE and the size of the tendon, we can calculate the bond length for that particular application, and we add the transmission length to the bond length to get the development length, which is the minimum length to develop the ultimate prestress, and that development length should be provided at the location of maximum moment. Next, we are moving on to the design of the end zone reinforcement. The prestress and the Hoyer effect cause transverse tensile stress, which is denoted as sigma T. This is largest during the transfer of prestress. Since there is a wedge effect, which is known as the Hoyer effect, there is a tensile stress developed in the perpendicular direction to the axis of the beam, which we are denoting as the transverse direction, and this tensile stress can cause cracking in the prestressed member. We may have to provide reinforcement depending on the amount of stress developed to check the cracking of the prestressed member. The following sketch shows the theoretical variation of sigma T. Towards the end of the member, when the prestressing is being transferred to the concrete, a transverse tensile stress develops, which is maximum at the end, and it drops down over the transmission length, and beyond the transmission length it is practically zero. Unless reinforcement is provided, there is a chance that this will lead to a cracking at the end of the member. To restrict the splitting of concrete, transverse reinforcement in addition to the reinforcement for shear needs to be provided at each end of a member along the transmission length. This reinforcement is known as end zone reinforcement. Thus, we provide some extra transverse reinforcement at the ends to check the splitting of concrete due to the transverse tensile stress. This reinforcement is in addition to the shear reinforcement that we provide near the supports. The recommendations of end zone reinforcement is based on the following two references. Both the references are written by Professor D. Krishnamurthy. The title of the first reference is A Method of Determining the Tensile Stresses in the End Zones of Pre-Tension Beams. This was published in the Indian Concrete Journal, Volume 45, Number 7, July 1971, and the pages are from 286 to 297. The title of the second reference is Design of End Zone Reinforcement to Control Horizontal Cracking in Pre-Tension Concrete Members at Transfer. This was also published in the Indian Concrete Journal, Volume 47, Number 9, September 1973, and the pages are from 346 to 349. The generation of the transverse tensile stress can be explained by the free body diagram of the following zone below a crack. The tension, compression, and shear are generated due to the moment acting on the horizontal plane at the level of the crack. Thus, for this pre-tension member, we shall look into a zone which is beneath as assumed crack level. The length of the zone is the transmission length, and in our next photo we shall see the free body diagram of this part of the beam. What we observe is that in this part there is a moment acting in the horizontal plane which generates a couple. There is a tension on the left which leads to the cracking, and there is a compression on the right. There is also a shear force. This part of the member is under equilibrium from the stresses that develops at the horizontal plane. The prestress, which has been transferred beyond the transmission length, and the prestressing in the tendon. This is under a self equilibrium, and there is a moment acting in the horizontal plane whose variation is shown in this graph. That means as we go along the depth, the moment is such that it creates tension on the left hand side, and it reaches a certain peak. After that, the moment drops down and it reverses in sign. That means beyond a certain level there can be compression on the left side. But what we are more interested is in the moment that creates tension on the left side, which leads to a splitting crack in the concrete. With this free body diagram, an expression of the amount of reinforcement has been suggested, which is based on the moment that acts in the horizontal plane. This moment can be calculated by the stress block which is acting above that horizontal plane. The end zone reinforcement is provided to carry the tension T, which is generated due to the moment M. The value of M is calculated for the horizontal plane at the level of CGC due to the compressive stress block above CGC. Thus, the procedure is that we are selecting the level of the CGC as the level of a probable crack, and at that level we are calculating the moment due to the compressive stress block which is above that horizontal plane, and based on that moment the tension can be calculated, from which we can provide the amount of reinforcement to carry that tension. The minimum amount of end zone reinforcement, which is denoted as AST, is given in terms of the moment as follows. AST is equal to 2.5 times m divided by Fs times h. Here Fs is the allowable stress in the transverse reinforcement, and this is selected based on a maximum strain. That means if we allow a strain up to say 0.001, then Fs is equal to Es, which is the modulus of the transverse reinforcement, times 0.001. Thus, depending on the strain that we may allow, we decide a value of Fs that is allowed in the transverse end zone reinforcement. H is the total depth of the section, and m is the moment at the horizontal plane at the level of CGC due to the compressive stress block on the right above CGC, and Fs is the allowable stress in end zone reinforcement. Thus, by calculating these values, we get an expression of the end zone reinforcement which needs to be provided within the transmission length to check any splitting of the concrete in that region. The end zone reinforcement should be provided in the form of closed stirrups enclosing all the tendons to confine the concrete. The first stirrup should be placed as close as possible to the end, satisfying the cover requirements. As we had seen from the variation of the tensile stress, the transverse stress, we found that the transverse stress is maximum at the end, and hence the first stirrup should be placed as close as possible to the end, satisfying the cover requirements, and the stirrup should be closed, which confines the concrete and helps to check the formation of splitting cracks. About half of the reinforcement can be provided within a length equal to 1/3 of LT from the end. The rest of the reinforcement can be distributed in the remaining 2/3 LT. Thus, since the stress varies quite rapidly at the end, we are providing half of the calculated end zone reinforcement in the first 1/3 of the LT, and in the second 2/3 of LT we are providing the remaining amount of transverse end zone reinforcement. Let us understand the design of end zone reinforcement by the help of an example. Design the end zone reinforcement for the pre-tension beam shown in the following figure. The sectional properties are as follows. The A area is 46,400 millimeters square. The moment of inertia I is equal to 8.47 times 10 to the power 8 millimeter to the power 4. The section modulus Z equal to 4.23 times 10 to the power 5 millimeter to the power 3. There are 8 pre-stressing wires of 5 millimeter diameter. Thus, AP is equal to 8 times 19.6 is equal to 157 millimeter square. The initial pre-stressing is as follows. FP0 is equal to 1280 Newton per millimeter square, and limit the stress in end zone reinforcement, that means which is Fs, to 140 Newton per millimeter square. As I said that the end zone reinforcement is being designed for the stress at transfer, because at transfer the chances of having cracks in the section is higher, and hence we are calculating the end zone reinforcement based on the pre-stress at transfer. Now, we observe that this section is a symmetric section about the horizontal axis. The CGC is located at half the depth. The flange width is 200 millimeters. The depth is 60 millimeters. The breadth of the web is 80 millimeters. The total depth h is equal to 400 millimeters, and the eccentricity of the CGS at the end is 90 millimeters. For this section, we have to design the end zone reinforcement given the amount of prestress at transfer. The first step is to determine the stress block above CGC, because we need to calculate the moment in the horizontal plane depending on the part of the stress block which comes above the level of CGC. In order to calculate the stress block, first we are calculating the initial prestressing force, which is P0 equal to AP times FP0 equal to 157 times 1280 newtons, which is equal to 201 kilonewtons. That's the initial prestressing force is 201 kilonewtons. Beyond the transmission length, the stress in the concrete at the top is given by the elastic expression Ft is equal to minus P0 by A plus the moment, which is P0 times the eccentricity E divided by the sectional modulus Z. The first term is negative because it is a uniform compression due to the prestressing force. The second term is positive for the top because the moment due to the prestressing force causes tensile stress at the top. When we substitute the value of P0, E, A and Z, we get that the stress at the top is practically 0, and we are not having any tensile stress at the top. The stress in the bottom is also calculated by a similar expression, where the second term is now negative because the moment due to the prestressing force is creating a compression at the bottom, and hence we are placing a negative sign for the second term. And again, when we substitute the values of P0, E, A and Z, we get the value of the stress at the bottom to be 8.6 Newton per millimeter square. Thus, for the section, we have determined the stress block, that it is 0 at the top and 8.6 at the bottom. Now we need to find out the moment at the horizontal plane, which is at the level of CGC, due to the part of the compressive stress block which is above CGC. For this, we are calculating the key values of the stress profile. One is at the junction of the flange and the web. From similarity of triangles, we can find out that the value of the stress is 1.29. The other key value is the level at the CGC, where the value of the stress is half of 8.6, which is 4.30 Newton per millimeter square. It is the top half of the stress block that we shall use to calculate the moment M. In order to calculate the moment, we are dividing the stress block into three parts. The top part, which is shaded orange, is in the flange, and for the part in the web, we are dividing it into two triangles, one the green and the other is the blue. This is to simplify the calculation of the moment due to the stress block. Now, for each triangle, we can find out the resultant compressive force. C1 corresponds to the resultant of the top triangle, C2 corresponds to the resultant of the green triangle, and C3 is the resultant of the blue triangle. We are also calculating the distances of the locations of C1, C2, C3 from the level of CGC, and these distances we are denoting as Y1, Y2 and Y3, because we need these distances to calculate the moment due to the stress block for the horizontal plane at the level of the CGC. Our second step is the determination of components of the compression block. C1 is equal to half of the stress at the junction of the flange and web, which is 1.29, times the area of the flange, which is 200 times 60. Thus, we get C1 is equal to 7.74 kilonewtons. Y1, which is the distance of the location of C1 from the CGC, is equal to 140 plus 1/3 of 60, which gives us Y1 is equal to 160 millimeters. C2, which is the area of the green triangle, it's equal to half times 1.29, which is the base, times the altitude, which is 140, times the breadth of the web, which is 80, which gives us C2 is equal to 7.22 kilonewtons. The location of the centroid of the triangle is 2/3 of 140, which is equal to 93.3 millimeters from the CGC. C3 is equal to the area of the blue triangle, which is equal to half times 4.3 times the area of the web, which is equal to 140 times 80, which gives us C3 is equal to 24.08 kilonewtons. Y3, the location of the centroid of the triangle, is 1/3 of 140, which is 46.7 millimeters. Our third step is to calculate the moment generated at the horizontal plane at the level of CGC due to the compressive stress block above CGC is given as a summation of C times Y. Thus, M is equal to sigma Ci times Yi equal to C1 times Y1 plus C2 times Y2 plus C3 times Y3. Thus, we are finding out the moment due to the individual compressive forces and adding them up to get the total moment about the horizontal plane. Once we substitute the values of C1, C2, C3 and Y1, Y2, Y3, we get the moment is equal to 3036.6 kilonewton millimeters. Thus, we have found the moment which is generated due to the compressive stress block above the level of CGC. Our fourth step is to determine the amount of end zone reinforcement. AST is given as 2.5 times M divided by Fs times H. Fs has been selected to be 140 Newton per millimeter square, and H is the total depth, which is 400 millimeters. M we have just calculated, which is 3036.6 times 10 to the power 3 to make it into newtons. Thus, once we substitute these values, we get AST is equal to 135.6 millimeter square. Thus, this is the minimum amount of end zone reinforcement that needs to be provided for this particular beam. With 6 millimeter diameter bars, required number of two-legged closed stirrups is equal to 135.6 divided by 2 times 28.3, where 28.3 is the area of 6 millimeter diameter bars, and when this is rounded off, we get 3 number of two-legged closed stirrups, and this needs to be provided within the transmission length. For plain wires, the transmission length LT is given as 100 times the diameter, and since we are using 5 millimeter wires, the transmission length is 500 millimeters. Provide 2 stirrups within distance about say half of LT, 250 millimeters from the end, and the third stirrup is in the next 250 millimeters. This is the way we are trying to distribute the end zone reinforcement, and we are providing more stirrup towards the end and less stirrup in the second half. The designed end zone reinforcement looks like this, that we are providing 3 additional 6 millimeter diameter stirrups which are closed, and it is enclosing the tendon, and out of the 3, the first 2 are provided in the first half of the transmission length, and the third one is provided in the second half. The first stirrup should be as close as possible to the end face. Thus, in today's lecture, we studied the transmission of prestress, and what we have found is that the transmission of prestress from the tendon to the concrete is different for a pre-tensioned and post-tension members. In today's lecture, we covered the transmission of prestress for a pre-tension member, and for a pre-tension member, since there is no anchorage device at the end, the prestress is transferred solely by the bond at the transmission length at each end of the member. We first studied the mechanism of the bond that develops between the steel and the concrete, and what we have found that the tendons which has surface deformations has a better bond, and for those type of tendons the transmission length is smaller. The transmission length depends on several factors like the surface deformations, the size of the tendon, the stress to be developed, the compaction of the concrete, but our code gives us a simple estimate of the transmission length which depends only on the size of the tendon. Now, the transmission length is the length over which the prestress is transferred to the concrete and the steel gains the stress from 0 to the effective prestress FPE. The second concept that we studied was the development length, which is required at the critical section of maximum moment, where the stress in the prestressing steel is FPU. Now, the development length consists of 2 parts. One is the transmission length and the second is the bond length. Along the bond length, the stress changes from the effective prestress FPE to the ultimate prestress FPU. The code gives us expressions for the bond length, which is in terms of the effective prestress and ultimate prestress, and the diameter of the strand, and a design bond stress. We need to make sure that the development length is provided at the location of the critical section. The third concept we studied was the end zone reinforcement, that there is a chance of cracking due to the transverse tensile stress, and to check the cracking we may need to provide additional stirrups, which is in addition to the shear reinforcement, and we saw a simple expression to calculate the amount of end zone reinforcement, and we saw also the application of that expression in an example. In our next class, we shall move on to the other type of prestressed member, which is the post-tension member. Thank you.